In today's functional analysis class, we are going to discuss resonance theorem. So first we state the theorem. So it is the theorem 9.3 in your text. Let X be a normed space and E be a subset of X, then E is bounded in X if and only if f of E is bounded in K for every f in X12. B. Let X and Y be normed spaces and f from X to Y be linear, then f is continuous if and only if G composition f is continuous for every G in Y12. Proof. A. Let E be bounded in X. That is, norm of X less than or equal to alpha for all X in E and alpha greater than 0. If f belongs to X12, then modulus of f of X is less than or equal to norm f into norm X. This is less than or equal to norm f into alpha for all X in E. So this implies f of E is bounded in K. Conversely, assume that f of E is bounded in K for every f in X12. Let J from X to X double dwell be the canonical embedding defined by Jx of f equal to f of X. X in X, f in X12. Then the set J of X such that X belongs to E is a subset of BL of X dash K, where X dash is a Banach space. Now for each fixed f in X12, the set of all modulus of J of X of f such that X belongs to E, this is equal to set of all modulus of f of X such that X belongs to E is bounded. Hence, by uniform boundedness principle, we see that the set norm J of X such that X belongs to E is bounded. And we have norm of J of X is norm X. Now since norm J of X equal to norm X for each X in X, it follows that E is a bounded subset of X. So we prove part B. Let f from x to y be continuous. Since every g in y12 is continuous, we see that G composition F is continuous. Conversely, let G composition F is continuous for every G in Y12. Let E equal to set of all f of x such that x belongs to x and norm x is less than or equal to 1 contained in Y. Then G of E is G composition f of ux closure, and since G composition f is continuous, G composition f of ux closure is bounded for every G in Y12. That is, G of E is bounded for every G in Y12. Hence, by part A of this theorem, E is a bounded subset of Y. That is, the linear map F is bounded on ux closure. Therefore, F is continuous by 6.21. So this proves resonance theorem. The statement 9.3a says that boundedness of f of E for f in x12 implies the boundedness of E in x. However, the convergence of f of xn for every f in x12 may not imply the convergence of xn in x. For example, you let x is equal to little l2 and en equal to 0, etc. 0, 1, 0, etc. for n equal to 1, 2, etc. Then you refer section 13.2. Then by 13.2, we can conclude that f of en converges to 0 for every f in x12, but en does not converge in x since 2 norm of en minus em is equal to root 2 for all n not equal to n. A similar comment can be made about the differentiability of function with values in normed space. So you see problem number 14.8. However, the analyticity of a Banach space valued function f defined an open subset of the complex plane C can be deduced from the analyticity of the function G composition f for every G in the dual of that Banach space. You can see problem 9.9. We have a second remark. Let x and y be Banach spaces and f from x to y be linear. Then 9.3b can be improved as follows. If the set G of S is a subset of Y12 such that GS composition F is continuous for every S, and for each Y in Y there is some S with GS of Y not equal to 0, then F is continuous. You can see it in problem number 10.8. So these are the two remarks on a resonance theorem. So that's all for today.